So good afternoon, ladies and gentlemen. So before starting, I would like to thank the other authors of this work, Professor Cornetti, Professor Carpinteri, and Professor Pierrao, all from Politecnico di Torino. So brittle materials and stress concentrations, are they able to withstand? So our analysis lies in the framework of brittle fracture in rounded V-notched elements. So we have a structure with a V-notch, and we want to investigate failure by properly taking the effects of the radius of curvature into account. The topic has been investigated for a long time by many different scientists, and we can distinguish basically the approaches, roughly speaking, into two main categories. Approaches based on stress requirements, both punctual or average, and approaches based on energy considerations. While approaches based on stress requirements are generally easier to be implemented since analytical approximative functions can be found in the literature, energetic approaches require basically the implementation of a finite element analysis. And nevertheless, the stress and energy conditions remain distinct, and so generally the fulfillment of one condition generally implies the violation of the other one. So the goal of the present work is twofold. From one point of view, the idea is to introduce or to apply a well-established criterion in order to match both the stress and energy considerations. And from the other one is to propose an analytical expressions for the stress intensity factor related to a crack stemming from the notch tip in order to implement also the energetic consideration in an almost analytical way. So this is the geometry. So that's a round V-notch. Rho is the radius of curvature, omega is the notch amplitude. This is the Cartesian frame of reference, and this is the polar frame of reference. The distance between the two frames of references is denoted by R0, which is provided by this expression here. So R0 is equal to 0, for rho is equal to 0. So it means if I consider a V-notch, basically the two frames of reference have the same origin. And also if omega is equal to pi, so it means for a flat, so a notch basically specimen, the two frames of reference coincide. And this is the finite fraction mechanics criterion I spoke about 2 minutes ago, introduced by Cornetti and co-workers in 2006. The criterion basically is expressed by two inequalities. The former is a stress condition. Test basically means that the stress resultant over a segment of length L must be greater than a function of the tensile strength, sigma u of the material, while the second conditions basically requires that the energy available for a crack of length L must be greater basically than a function of the fracture energy. Here I wrote the relationship in terms of the stress intensity factor K1 and the fracture toughness of the material K1C by applying the well-known Ewing's relationship, and our analysis will be limited to mode 1 loading condition. It means that the crack will propagate along the notch bisector. So if we want to implement this criterion, we need two functions. One is the stress field, sigma y of x, and the other one is the stress intensity factor function. So there are no problems for what concerns the stress field. I mean, no problems because these expressions was proposed by Philippe et al. In a work of 2002. Here K1V is the generalized or notch stress intensity factor, while the other parameters, lambda, mu, and eta theta of zero, depend on the notch opening angle omega, and they can be found and tabulated in the work by Philippe et al. Of course, for omega is equal to 0, so it means we are facing the case of a U-notch. The well-known Krieger-Paris expression is achieved. While for rho is equal to 0, it means a V-notch, there is not a radius of curvature. The stress field reduces to the asymptotic expressions provided by Williams. So the stress field basically is this one. On the other hand, for what concerns the stress intensity factor function, in 2011, to be honest, we proposed this expression without m, and in 2014 we refined this expression by introducing m. All these parameters can be found tabulated in the literature. For instance, beta here, that's the geometry, sorry, this is C is the length of a crack stemming from the notch tip, and C is supposed to be basically lower than the notch depth, which was denoted by A. This expression without M was introduced in 2011 to match basically the asymptotic limits of very short cracks. In this case of very short cracks, the problems reverts to, the geometry reverts to an edge crack subjected to the local peak stress, so this expression is currently recovered. And in the case, on the other hand, of a very large crack length, but still smaller with respect to the notch depth, basically the expression of the stress intensity factor stemming from a V notch is again consistently recovered. This expression was proposed by Azebe and Lila in 1978, and the parameter beta can be found also in a recent work, a more recent work by Olivieri and Toro. So this was the original basically expression, and then we introduced this parameter M in order basically to refine our results, to improve predictions. So this is Omega, the notch amplitude, Williams eigenvalues, the beta values provided in the work by Azebe and Ida and Olivieri and Toro, eta theta function found in the paper by Philippe et al. And these basically are the values that we estimated in our work in 2014 as a function of omega. In order to estimate M, basically we performed some simple finite element analysis by means of French UGR code. This was basically the geometry for, I think, 90 degrees. The ratio between the radius of curvature and the notch depth was 1/100, and the ratio between the notch depth and the characteristic length of the specimen was 1/100, and then we consider tensile load. We consider then a crack, basically stemming from the V notch. The mesh was refined by the software, and then we evaluated the stress intensity factor for different length, for different crack length. And these are the results, for instance, for omega is equal to 60 degrees. This is the dimensionless stress intensity function as a function of the dimensionless crack advance. So the black data represents the numerical data. The black thick line represents our current, basically, predictions. The thin line represents the prediction without considering the parameter M, while the other two curves represents the asymptotic limits of a very short crack, this one, and a very long crack. As it can be seen, basically the greatest error was more or less around 5%, and now it's quite zero. I mean, it's less than 0.5%. So now we have the stress field function, we have the stress intensity function. We can basically suppose that failure takes place when this condition is satisfied, which means when the notch stress intensity factors basically reaches its critical conditions, so it's equal to the apparent generalized fracture toughness, which depends, as denoted here by rho, on the notch root radius. So by substituting the two functions into the finite fracture mechanics systems, we get these two equations. This is a system of two equations in two unknowns. One is the failure load implicitly described basically by the apparent generalized fracture toughness, and the other one is LC, which is the critical crack advance. So basically it's a system, we can basically solve it, we can equal both expressions with respect to K1C rho, and we get these expressions. And so now when the material properties K1C and sigma u are provided, when rho and the notch amplitude, which are basically described by rho 0, are known, we can derive the function, the LC values, and then we can substitute this LC into either this condition or these conditions in order to get basically the failure load. Just one thing, by introducing M, this expression G basically is described by an integral which cannot be solved analytically, so of course the problem is not a big problem, but just to be honest, you cannot proceed in an analytical way, basically, as done before without considering M. And these are some results, theoretical results. This is the dimensionless apparent generalized fracture toughness with respect to the generalized fracture toughness, the expression of which can be found in this work by Carpenteri and co-workers, as a function of the dimensionless notch root radius. As it can be seen, the failure load increases as the notch root radius increases, as basically the material properties change, becoming more brittle, and of course it changes as the notch amplitude changes, becoming more significant for lower notch amplitude. So for a crack, basically the effects are greater than for an angle equal to 150 degrees. And these are some, basically the theoretical results for what concerns the dimensionless crack advance as a function of the dimensionless notch root radius. So as it can be seen here, differently from the criteria based only on stress or energy considerations in this case, the crack advance becomes a structural parameter, so it depends both on the material properties and on the geometrical features. As it can be seen here, is a function of the notch root radius, and it varies along with the angle. So this is a property related to fine fracture mechanics. And finally, eventually, basically, we consider some experimental results available in the literature. For what concerns U notches, so MIC is equal to 0, we consider this material aluminium, and these are the material properties which were measured in this work. And for what we consider also this squenched AZ4340 steel, which was heat treated, and basically we consider two different tests, one performed by Rich et al. In a work date 1976, and one performed by Firao and co-workers, and here is 1978, 1982. The material properties were a little different, one with the other ones. And eventually, for what concerns round V notches, we consider this case PMA test on -60 degrees, and these are the material properties which will be implemented. So now, this is the experimental validation for what concerns the case of U notch. That this is the apparent basically fracture toughness as a function of the dimensionless, basically the square root of the dimensionless notch root radius. These are basically experimental data referring to alumina, to steel test by Firao, to steel test by Ricci. These are basically the theoretical predictions according to fine fracture mechanics by considering the parameter M, and these are basically the predictions by fine fracture mechanics without considering M. There is basically a general improvement. As it can be seen, the differences can be noted. There are some differences, especially here next to rho equal to 0. Where now M, by introducing M, there is, as it can be seen, a more flat behavior, and this is more consistent with a lot of experimental data which show a minimum here, close to rho is equal to 0 degree. Eventually, there are some discrepancies here, because here, basically, the notch root radius is greater, so in this case, is not so small with respect to the notch depth. So basically our asymptotics analysis, our asymptotic stress field and our asymptotic stress intensity factor functions are not precise. So if we want to implement fine fracture mechanics in a more precise way, we need to substitute the whole stress field and not its asymptotic expansion. And these are the results for what concerns omega is equal to 90 degrees, PMA test at -60 degrees. In this case, the picture is not dimensionless, so and it's a function of rho and not of the square root of rho, so it changes the curvature, but the predictions are accurate, as it can be seen. And this is basically the situation for what concerns 150 degrees, and the same considerations that I did before for 90 degrees hold true. So in order to conclude, basically we apply the coupled energy and stress manufacture mechanics criterion to brittle round V notch structures subjected to mode 1 loading conditions. So whereas the stress field function is already known in the literature, an original expression for the stress intensity factor was proposed. And basically it improves by means of the parameter M generally finite factors mechanics predictions. Eventually we basically compare theoretical predictions with experimental data, finding generally basically a good agreement. Thanks for your attention.